Okay, welcome back. More review stuff. So we'll begin. This is 1.5, and this time we're just looking at inverse functions in general. So there's going to be a lot of groups of functions that we take a look at, and we'll want to be able to do operations on these functions. And you're probably, well, I hope you took trig. So if you took trig, you would have had to dealt with sine functions, cosine functions, all that jazz. Let me plug the mic in. Sorry, hopefully you could hear that. So inverse functions, and I'm talking about we're going to have to work with basically groups of functions. We're going to be doing things to these functions, and we want the complete picture basically. So if you should have had taken trig, and when you took trig, you probably dealt with sine functions, cosine functions, and that sort of stuff. And with those functions, you could also deal with the sine inverse, cosine inverse functions. Okay, so for the complete picture of calculus, we want to deal with all of those guys, and so it's just like in math. You dealt first with, arithmetic. You first dealt with things like 3 plus 3, and then 3 plus 5, and then eventually, what plus 3 would give you 0. So it's additive inverse. Now here we're looking at the sort of functional inverse. Okay, I'll shut up. So section 1 here, we define the inverse functions with these things called the cancellation equations. And we say G is the inverse of F. If, when you do a composition of the function, so f of g of x, you end up with x for all x in the domain of g. And then if you put f of x inside of g of x, you also end up with x for all x, and then in the domain of f. Okay. Okay. So, let's take a look at a more, a more unusual example, I guess. I wouldn't call it unusual, but it's not as straightforward. Here we have the square root of x minus 4. We want to know what its inverse is. Well, I guess they already gave us the inverse in this problem. Sorry. So they want us to verify that g of x is in fact the inverse of f of x. I say it's an it's a more less straightforward example, because in order for this thing to be invertible, in order for this to be the inverse of this, we actually have to have this restriction that x is greater than or equal to 0. Okay? Otherwise, this guy won't technically have an inverse. Okay? It won't be 1-to-1, and we'll talk about that here in a second. Okay, so anyways, here the implicit domain, you need x minus 4 to be greater than or equal to 0. So you need x to be greater than or equal to 0. So implicitly, the domain is implied to be from 0 to infinity. Okay. Likewise, then we could go and get the range. If you recall, graphing these things via translations, the square root of x function is this guy. And then to get the square root of x minus 4, I can just shift this thing over 4 units. And then that would be my graph of this guy. Okay, that's this guy. So in this case, the range is the possible y values. So you kind of think of compressing this graph onto the y-axis, and there would be residue from 0 to infinity again. Okay, so over here for this guy, the graph, if we want to go and graph it, we can, I guess. Might as well. It's just the parabola shifted up 4, so it should look like this. And then the domain is given, so that's not exactly the graph. The domain from 0 to infinity suggests that we're not actually looking at this part here. Okay, this part here we're going to kind of scratch out, and we just consider the right-hand branch of the parabola. Maybe I should circle that like in a different color or something. I don't know. Here it is. There, that's the part we want. Okay, then the range, and again, I'm just kind of looking at the graph for this. The vertex is at 4, 0, 4, so it's going to go from 4 to infinity. Okay. All right, so I want to verify that these guys are inverses of each other. And, you know, I'm going through this domain issue. I guess I got the range just for completion, but I need to have the domain to verify that this is true for all x in a particular domain. It's something that you probably wouldn't have done in maybe college algebra unless your teacher was a real monster. But let's take a look. So f of g of x, f of g of x. Yeah. Taking this thing, oh, whoops, vice versa, right? This thing, and I'm putting them in here. So I'll have the square root of, replace x with x squared plus 4, and then we'll go minus 4. 4 minus 4 is 0, and then has square root of x squared. And again, that's one of those technical issues, right? The square root of x squared is not just x. It's the absolute value of x. Okay, so technically, this thing really isn't equaling out to x. But then we consider the domain. So as long as it's true for all x in the domain of G, so what is the domain of G? That's 0 to infinity. As long as it equals x for this domain, we're good. And in fact, it does. The absolute value of any x in the domain here is just x, because all these guys are positive. Put absolute value of 5, that's just 5. Absolute value of 10, that's just 10. So yeah, this one works for the given domain of G. Big D, little g. I'm just making up that notation for the sake of sanity, so I don't have to write out the domain of G all over it. Okay. Then let's look at plopping this guy into this guy, g of f of x. So wherever I see x, I'm putting square root x minus 4. So square that, and then plus 4. There is an implicit domain here of, for f of x, it's 4. We need, oh geez, I screwed that up, sorry. So this has to be 4, sorry, I got that. Right, sorry about that. So, you know, add 4 to both sides of an inequality, what do you get? Well, you get 4 over here. Okay, great. So, you know, as long as you're in that interval, this is fine. You could square it, and you'll end up with just x minus 4, and carry over the plus 4, and definitely that'll work for all domain, for all x's in the domain of f. Okay. All right, so that's a more unusual one. Usually you don't have to worry too much about the domain. You'll just be working with polynomials or something like that, but that was a more, okay. Let's take a look at how or when these things actually have inverses. So we're talking about the existence of inverses. And in particular, you need these guys to be one-to-one. And one-to-oneness is a quality kind of like functions, or a quality of relations. So you need these things to well, we could take a look at an arrow diagram. It'll come down to a horizontal line test, really. So something that's one-to-one is considered extremely well behaved because it's already a function. You've assumed it's a function. And then on top of that has this other quality such that for every value y in your range, there's only one corresponding x over here in your domain. So you wouldn't have some value in the domain and two values in the domain going to the same value in the range. Okay? So this is 1 to 1, and I'll write 1 to 1 with numbers 1 1, and this is not. And it's not because of this issue here. Okay? It's like you want it to be a function in both directions. You want it to be a function this way and then a function this way. And this wouldn't be a function in the other way because you have this splitting going on. Okay, okay, so there's different ways to prove this thing. There's algebraic ways, which you know, the algebraic method, which we don't get too carried away with these kind of proofs, but they are out there. Let's say, for example, prove that an equation of a line, say 3x plus 1, is 1 to 1. Okay. So if a function is 1 to 1, then you say f of x1. So how does it work? If f of x1 is equal to f of x2, then it must be the case that x1 equals x2, because you can't have two different x values going to the same y value. Okay? So our proof of this thing, we suppose sort of x1 and x2 are particularly the arbitrarily chosen real numbers. Okay. Note then f of x1 equaling f of x2 suggests that 3x sub 1 plus, I just do a substitution, equals 3x sub 2 plus 1. And our goal is to show algebraically that x1 and x2 are the same. So you subtract 1 from both sides, you get 3x1 equals 3x2. Divide by 3 on both sides, x1 equals x2. And that's what we wanted to show. In other words, if x1, f of x1 equals f of x2, then x1 equals x2 follows. Okay. So that's sort of our algebraic version of the proof. I won't expect you to be able to do that, but just be aware, like if you become a math major or something, that should be easy for you. Anyways, the way we will generally think about this is the horizontal line test, right? So we're all familiar with the vertical line test. But the horizontal line test, you know, it's going to be from 1 to 1ness. So things that are functions are not necessarily going to be 1 to 1 anymore, or not going to necessarily be 1 to 1, because it's going to fail the horizontal line test. It hits it in two places. In other words, for this one particular y value, there's two different x values going to it. And that's what the horizontal line test is really saying. Okay, so this is not 1 to 1. And this is you know, a second degree polynomial, which is what we were working with back there in problem 5 at the beginning. And in order to get around this not 1 to 1ness, we had to restrict the domain. Okay, and that's what we're going to have to do for the trigonometric functions, which we'll see here in a bit. So anyways, this is not 1 to 1. Something that is 1 to 1 would be like your exponential function, okay, y equals b to the x, right? So you know from college algebra, this guy is invertible, and the log base b of x is its inverse. So as long as it's 1 to 1, that's going to mean it's invertible, and vice versa. So if you have something that is invertible, it is one-to-one. Okay, so it goes both ways. Let's look at 24 and see what we're dealing with here. Determine if this thing is one-to-one. We have y equals sine of 3x over 2. Okay, so the amplitude is 1. The period, to find that, we just take the 3x over 2 and wedge it in between 0 and 2 pi. Okay. And solve for x. So we would get x 4 pi over 3 for our period. And then to get the tick marks, just divide that by 4. So our tick marks will be at pi over 3's. Okay. So 4 pi over 3 divided by 4 is pi over 3. So I can come over here and I can graph it, because I'm going to apply the horizontal line test to it and see if it works. And I think most of us know, hey, it's not going to work. But we need a little practice graphing trig functions for Calc 2. So anyways, its amplitude is 1. And there we go. We're going by pi over 3. So obviously already it's not going to pass the horizontal line test because of this issue right here. So it's not one-to-one. Okay, but however, we have seen that if it's not one-to-one, we can make it one-to-one, like in question 5, by restricting the domain. And if you took trig, which I assume you have, you know that the workaround is to restrict the domains of the particular sine and cosine functions. Okay. So we want to review that material. The inverse functions, inverse trig functions. And we'll take a look at cosine's graph. So cosine, of course, starts up here at 1, going by pi over 2's out to 2 pi. It'll look like this. And there's 1 period. It fails the horizontal line test, so what do? You restrict its domain from 0 to, let's see if I can get a nice pen with a different color, 0 to pi, right? So the restricted domain is going to go from 0 to pi, and in that regards, then we can go ahead and find its inverse, the graphical inverse of cosine, just by rotating this thing about the line y equals x. Okay, so it's not entirely easy or intuitive the way it's shaped, but at the end of the day, you're going to end up with this character. Okay, it looks like that. And of course, we're going from -1 to 1, and this is at pi over 2, and then this is up here at pi. Okay. So the domain here is -1 to 1, and then the range 0 to pi. Okay. And of course, this is cosine inverse. So in the book they'll show you the other ones. Probably for some of the problems here, the most important thing is going to be the range of these functions. So I'll just note that here. So for y equals cosine inverse, the range, and I'll do sort of a unit circle graph looking thing. The range is going to be from 0 to pi. For y equals sine inverse of x, the range is going to be from -pi over 2 to pi over 2. And then the only other one we really need to worry about, you could really beat this stuff to death if you wanted to, but we'll just stop at tan inverse. That's from negative pi over 2, not including that, all the way to pi over 2, because there's asymptotes involved. So, okay, let's go ahead and take a look then at some of the problems in your homework that revolve around these issues. 87, they want you to figure out the arc sine of 1/2. Okay, so the output, and why was I worrying about the range? The output of this thing is going to have to be in this range. So I kind of like to draw a picture to remind myself of that. Okay, it's from negative pi over 2 to pi over 2, and you're asking yourself the sine of what angle equals 1/2 in that range. Okay, so really this is asking for x in this equation. So you have to remind yourself, okay, that's pi over 6. The reference angle, it's positive, so it's pi over 6 is about right here, and that'll be our answer. Okay. So yeah, you do have to kind of remember your reference angles. Hopefully you do. You can kind of cheat a little bit with your calculator, but anyways. What's the arc sine of 0? Again, the output is going to be in the range from negative pi over 2 to pi over 2, and we're asking ourselves the sine of what angle is equal to 0. Obviously, there's more than one angle, but we just want the angle in this range, and that would be 0. Okay, so that would be 0. Let's see, number 90. These are all extremely easy, almost so easy that it's not very instructive. Anyways, our cosine, so you're asking yourself the cosine of what angle in the range from 0 to pi is equal to 1. You know, the cosine of one angle is equal to 1. And again, that's just going to be 0. Yeah. Let's see. Using right triangles. So this is something that will come up later in Calc 2. So you probably have to review it again. Let's just take a look at it right now. Hopefully it'll be there for you later on. Using right triangles then. What are we dealing with? So let's look at 107, part A. We want to figure out the sine of arc tan of 3/4. Okay. So with the arctan of 3/4, you could consider the input as a ratio of sides of a right triangle. So maybe try to abbreviate here. You have a right triangle. If you're dealing with tan, well, what's the deal with tan? Tan was opposite over adjacent, so it's the ratio of sides of this little triangle here, opposite over adjacent. And you just use the numbers in here to fill out the sides of the triangle. So there's a 3, 4, 5 triangle. Okay. And then the sine of this whole thing is the angle inside this triangle. The sine of that is going to be opposite over hypotenuse, so you end up with 3/5. Okay. Let's look at another one. This is 109. It's part B. So here we have the cosecant of arctan of -5/12. Okay. So if you need to, you can embed these things in little unit circles to deal with the negative portions. Remember, arctan, its output is going to exist in the between negative pi over 2 and pi over 2. So you could kind of draw a unit circle in that range and embed the triangle into this unit circle. Okay, so I'm not going to be writing, so what is this? Arctan is opposite over adjacent. So I'm not going to put opposite as positive 5 and then go negative 12 this way. I'm going to go opposite down 5 and then adjacent is the 12 right here. Okay, so our triangle will kind of look like this, where the adjacent side is the negative 12. Okay, and then the opposite is 5. Then for your cosecant, cosecant is 1 all over sine. You're thinking hypotenuse all over opposite. So I need this side here, which will be positive 13. And then, the cosecant again, this should be positive 12. This should be negative, sorry. It's 1 over sine, so it's hypotenuse all over adjacent. So, sorry, hypotenuse all over opposite, so it's negative 13/5. Okay. So those are a little bit more challenging. Ultimately, this issue of the positive and negatives doesn't really come up in the work we do. So that's even why I was kind of struggling a bit with it. What we'll want to do is take kind of these trigonometric expressions and turn them into more algebraic type expressions. So for example, 1, 1, 1, we have the cosine of arc sine of 2x. And we want to rewrite this as an algebraic expression. And what we do is use a triangle sort of gateway to do that. So we consider this as a ratio of sides of a triangle again. So 2x is the same as 2x over 1. And then I build my triangle off of that. So here's my angle, arcsine of 2x over 1. The sides then for sine, it's opposite over hypotenuse, and then use Pythagorean theorem to solve out for the third side. So 1 squared minus 4x squared. Right? Finally then, cosine of this is adjacent over hypotenuse, so we can rewrite this expression as 1 minus 4x squared, which is what we'll be needing to do ultimately. Okay? Let's try one more of those, and then I think that's good enough. Well, and then we'll do an inverse problem, sorry. 115, here we have tan inverse, or rather tan of arc secant of x over 3. Okay. So we'll use arc secant of x over 3 as our angle here. Secant is 1 all over cosine, so that would be hypotenuse all over adjacent. And then the third side of the Pythagorean theorem is x squared minus 9. Okay. And then tan of this triangle will be square root of x squared minus 9 all over 3. Sorry. Okay. Okay, so that's the idea. Hopefully it won't be lost in your memory banks by the time we actually use it. Anyways, let's just do one where we find the inverse of a particular given function. And again, this will be one of those radical ones. So f of x is equal to square root of x. So in order to do this appropriately, I need to kind of be cognizant of the domain. And here we have an implied domain of 0 to infinity, because the guts of the radical need to be greater than or equal to 0. So the domain is implied to be from 0 to infinity. And then the range, just from my knowledge of what the graph looks like, so will also be 0 to infinity, right? Because this thing looks like this. Okay. I need to find the inverse. So here I'm going to actually do the swapping of the variables. So originally, it's y equals x square root x, and then I swapped the variables, x equals the square root of y, and solved for y. Right. So square both sides, you get x squared equals y, and then you're done, right? Y in this case is x squared. This is kind of a problem though, because this guy right here, this y equals x squared, is not really invertible. So how is it to be an inverse of something if itself is not invertible? And what we will have to do then is restrict the domain for this to work. So the light blue portion over here is going to have to be omitted for this to pan out. And then in particular, we'll note that the domain here, in order for this thing to be the inverse, is actually 0 to infinity. Okay? And then, of course, its range is also 0 to infinity. So that will be the inverse. It's not the parabola. It's not the complete parabola picture. It's just part of it. Okay. And then clearly that's kind of, if you know about how to generate the curve, the inverse curve, via just rotating it around the line y equals x. So there's my line y equals x, and I do a rotation. The resulting rotation is just this curve right here, right? So there's my rotated version, and it is, we exclude this portion, and all we have is this arm of the parabola. Okay. So I'll leave it at that. Hopefully that'll work. Okay, thanks for watching. Bye.